So, the question this time has asked us to implement a soft XOR gate as given in example 1.7 in the textbook. Okay, before we do so, it's important you have the BRML toolbox. This, how you can get it, has been explained in another video that has been linked to this video, so do make sure you have it. And once you have the BRML toolbox, you do have to remember to run setup.m before you can actually do anything. So let's start. We want a function for soft XOR. I'll just call it this. First thing we have to do is import the toolbox. So import brml.star. Okay, so we have two input variables, a and b, and an output variable, c. All of these variables are binary variables, so they can take only one of two values, 1 or 0. I'll refer to these as on and off, because that's a nice way of referring to any kind of logic gate or state of a logic gate. And the variable names themselves are a, b, and c. I'm going to introduce some numbering, so I can use it in the table notation later on. This is just arbitrary, so I'll write that down. Arbitrary variable numbering, and then I'll say a is equal to 1, seems sensible, b is equal to 2, that's natural, and you can probably guess c is equal to 3. We also have to define the states starting from 1 in MATLAB. It's not like many other programming languages which have indices beginning at 0. MATLAB starts at 1. So I'm going to say on is equal to 1, and off is equal to 2. Let's define the variable domains. So I'll put that in a comment. It's always good to comment your work. Variable domains. And we first have variable a dot name is equal to simply a. And we can also define its domain. Dot domain equals, as we said, on and off. On and off, quite simply. I have to repeat this for the other two variables, b and c. I'm just going to copy and paste this, so I'm just changing small things. Control V, Control V. These are b, oops, c, C, B, B, it's quite tedious, B, and that seems okay. Not too happy about the red underline, but I guess that means we haven't used the variable yet in MATLAB. Now what we have to do is exploit the fact we know that A and B are independent. So what we're going to say is, I know that because the joint distribution in general can be expressed as probability of A, B, C is equal to probability of A times the probability of B given A times the probability of C given A and B. We can actually exploit the fact that we know B is independent of A. So let's remove this. And now we have three potentials to define: potential 1, potential 2, and potential 3. Let's begin by defining potential A. So I'm just going to write that. Define the potentials. Quite simply, potential A is equal to an array. So this is quite from scratch. Then I also have to define that potential A dot variable. So there's only actually one variable in this, that's A itself, is equal to A. And now we have actually defined the values in the table. So potential A dot table, the value of on, so index on is 1, the first one. We are told in the actual example 1.7 in the textbook, the value is 0.77. Oh, sorry, that was for B. For A, it's 0.65. Pardon me. That quite simply makes our potential for A in the state of equal to 1 minus 0.65 minus 0.65. Not too difficult. If you want to be more like programmingly correct, instead of writing 1 minus 0.65, you should write 1 minus potential A dot table on. But that's long to write, so I'm going to skip that. Potential of B is defined in a very similar way, so I'm just going to copy paste this bit to save myself lots of typing. And just write B everywhere. B, 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 B. This is B. And now it's 0.77. And this is where I should have kept the correct programming strategy, because I wouldn't have had to change it in 2 places. But I'm too lazy for that, and I'm only doing it as a one-off, so it's fine. And finally, we now have to define the potential for C. C's potential actually includes all 3 variables A, B, and C, because C is conditional on A and B. We're basically defining the probability distribution of C given A and B. So to begin, potential of C is equal to array as before. Now we have to find the variables. Potential C dot variables. Oops, what's going on? Dot variables is equal to C, A, B, because we want C conditional on A and B. The order is in a way arbitrary, but this makes it kind of intuitive to understand, because we're always saying the probability distribution of C given A and B. So this is define the variable order. I'm just going to write that here. Define the variable order. Now we can start populating our table. I missed a semicolon here. We don't want to do that. So potential of C dot table. Let's first consider the case. We're always going to consider the case C is on first. So C is equal to 1. C is on, A is off, and B is off. And we are told by looking at the table in example 1.7 this value is 0.1. i.e. the probability of C being 1 given A and B are 0 is 0.1. I'm going to copy this construct and reuse this below. This time when we consider the case, we have B being on. And we now know in the setup it's 0.99, is referring to the table in example 1.7 in the textbook, as mentioned before. Now let's consider the case on off. So A is on, B is off, and we have 0.8. And now let's consider the final situation where A and B are both on. And we are told in this scenario the probability of C being on, given that A and B are both on, is 0.25. Okay. Now, we haven't actually finished populating the table for C because we haven't considered the situation C is off. It would be quite long to write out these 4 statements again, so I'm just going to use a very simple trick and populate them all in one go, knowing that the probabilities of each conditional sums to 1. Probability of C dot table, and I'm going to refer to the correct indices, so off and all indices here and all indices here for A and B is equal to 1 minus the potential of C dot table, what we've done so far. So basically all the 4 above values. So always where C is on, and we want all the values of A and all the values of B. I can say because probabilities sum to 1. That's like just a reminder what happened. Now we want to write the joint distribution. So let's say joint distribution, which we know is simply the product of potentials, as defined earlier over here. So the joint distribution, we can use a function called joint pot, multipots. We'll just call a variable joint potential. Joint pot is equal to multpots. That simply means multiply the potentials. Pot is the object name. That's quite simply done. And now I want to actually work out, as given in example 1.7, is what is the probability distribution of A given we know C is off. Specifically, the question asks us for what's the probability of A is equal to 1 given C is equal to 0. So what I'm going to display, disp, is P of A given C equals off. That's all I'm displaying. And this is quite a simple function we can use. So I'm going to go display table, disp table, and I'm going to use another function called cond_pot. So it's a conditional potential, cond_pot, where I am going to set the potential of joint pot as defined, and I want to condition C. So I want C, variable C, to be set to off, conditioned on the variable A. I think I've typed everything correct there. MATLAB seems to be giving lots of suggestions, but I think I've managed. And I think that's it so far. So we'll see if this gives the same value as the textbook. The textbook, they found that the probability A is equal to on given C is off is 0.8436. So I'll try that. Looking for 0.8436. Before we run this function, I do have to save it. I'll save it as soft XOR, sure. Okay. I already have a function called soft XOR, so I'll save it as my soft XOR. That should do the trick. Save. Okay, let's see if this works. I'll just type in my soft XOR. And excellent! It says the probability A is equal to on given C is equal to off is 8.435848 times 10 to the minus 1. And that is 0.8436 as we were looking for given in the textbook. So there we are. We have successfully implemented the soft XOR gate given in example 1.7 in Barber's textbook. And that is that.